Welcome to Empowered Learning. This is the second video of the video series for solving first order ordinary differential equations using substitution techniques. So in this video, we are going to study what's called homogeneous equations or homogeneous equations, depending upon how you want to say that word, which we use what we call rational or fractional substitution to essentially be able to take these types of equations and force them from being what they are, which is homogeneous or homogeneous, to either being a separable or first order linear, type of equation. And so more times than not, our goal is to take a homogeneous equation and do the proper substitution to force it to be separable. Now, when we talk about a homogeneous equation, we need to know what it is that what we actually mean. So we're going to go ahead and define that here and get some practice on verifying that a particular ordinary differential equation is homogeneous, and then after that we'll do some examples of actually solving. So a homogeneous equation of the first order is an ODE of the type that looks like what you see here. So it's dy over dx is a function composed of both x and y, but this is a special type of function of x and y in that it could also be rewritten this way, And so essentially what we're saying here is that if I was able to replace x with some real number times x, and I was to replace y with that same real number times y, substitute that into the right-hand side of that particular equation, and I still ended up with this at the end of the day, then I know that it can be what we call a homogeneous equation, Now, why is that important? Well, we know that if our function on the right-hand side of our first order differential equation here can be rewritten like this, but it's still the same as this, then what this means is that we can ultimately rewrite our homogeneous ODE in separable form, So by us being able to do this test here to see, hey, let x be some number times x, let y be that same number times y, work out and simplify what that function of both x and y would be, and if it will turn out to be the same thing as it would if we didn't do the substitution, then we know it can be rewritten in a separable form, Now, in order to make this happen, though, the type of substitution that we need in order to make this possible is to let u be our substitution, u be y divided by x, Or put another way, let y equal u times x, and u is going to be assumed to be a function of x. Not just a real number like how the t was, but it will be an actual function of x. So essentially what we're saying here is that y is going to be a product of two functions, one of which is going to be some unknown function u of x, and another one is going to be x on its own. And we're going to say, the reason why we're saying u is unknown because we don't necessarily know what y is, but we know that u is going to be whatever the solution is divided by x. And so that's our basic strategy. So once we recognize that an ordinary differential equation of the first order is a homogeneous one, then we can use the substitution of letting basically y equal u times x in our equation, or if we see somewhere where we have y divided by x, we just let that be u. Again, do the same kind of thing that we did before with the linear substitution. Once we make the substitution, we want everything written in terms of either u and or x, So that means if we already have y that's going to be rewritten in terms of u and x, so that means we need to find the derivative of y and rewrite that in terms of u and x. So that's the basic idea. All right, so for our next few examples here, we're going to look at some first order ordinary differential equations and determine if they are going to be of the homogeneous type or not. And we need some practice at this just to make sure that we understand how to actually go about testing this. And another thing I want to make clear, because I know I've said this in other videos, but I'm going to say it in this one as well. In general, you need to be able to know the types of equations that you're dealing with. Okay. If you're trying to study for a course like this, the very first thing you should do, other than just make sure that you know your prerequisite basics, is to say, all right, when I see an equation, do I recognize what type it is, or do I recognize that I can manipulate it to be in a certain type? So that is number one. Once you know what type of equation you're dealing with, then you know what type of techniques you could use to solve that equation. If you have no idea what type of equation you're dealing with to begin with, you're going to be lost on what to do. Okay. And this body of knowledge called differential equations, that's essentially what it is about. Recognizing equation types, knowing what to do based upon that equation type. Okay. All right. So for this first example here, we want to test to see whether this particular function is homogeneous or not. Okay. So essentially what that means is everywhere where we see x, we're going to replace it with tx. Everywhere where we see y, we're going to replace it with ty. So this would be ty here. That will be tx there. And of course, our goal is to do all of that and see, are we going to get this original thing on the right-hand side again? Okay. So that is the basic idea. So I'm going to go ahead and erase all of that. And we will see what it comes out to be here. So we replace x with tx, y with ty everywhere. And then we just try to work it out and simplify as much as we can. Okay? So once we actually square this term here, then we see that we can factor out a t out of both terms here. Of course, we got a t squared here. So t divided by t squared is just 1 over t. And we look here, okay? Now, the issue that we're having here is that what you see here is not the same thing that you see there, because there's not much more simplification we can do. And we see that since this does not match this, then this would not be a candidate for what we call a homogeneous first order type of equation. Okay, so we wouldn't be able to use the techniques that we just got through talking about to solve this one. All right, so let's move to the second example. This one does end up being homogeneous. So of course, if we do the same thing again, if we let y be ty, x be tx, we see that happens here. Each of these I can factor out a t out of the numerator, and of course this t and that t reduce to 1, and we essentially get the same thing that we started with. So for this particular type of ODE, the right hand side of it lends itself to being allowing us to say that this entire ODE is of the homogeneous type. So because of that, what I am allowed to do if I was going to solve this particular ODE is I could say y is just equal to ux, okay? Or if you want to do it another way, let u equal y divided by x, okay? And substitute that in here as needed, and then you just go to work. And by doing this substitution here, what we're doing is actually forcing this particular ODE to be a separable equation, okay? All right, so let's move on to the next example. All right, so for this example, same thing. We want to test to see whether this particular ODE is going to be homogeneous or not for this first order ODE. And we see here that this is a function of both x and y. And what we want to figure out is, can this be also rewritten this way, okay? So to do that, we just say f of tx, ty. Everywhere where we see x, we're going to rewrite it with tx. Everywhere where we see y, we rewrite it with ty. And all that over x, which is just tx, and y with ty. So we do that. Of course, in the numerator, we'll have t squared x squared plus 2 times t squared y squared all over t squared xy. And of course, you can kind of see that this should work out here because we have a common factor of t squared in both terms here in the numerator. Have the same thing here in the denominator. So if I factor that out, I'll have x squared plus 2y squared here. All that over t squared times xy. This just reduces to 1. And here we end up with what we started with on the right-hand side. So this is a first order homogeneous ODE. All right, so for the last example where we're going to verify whether our ODE is homogeneous or not, we're going to do the same thing. So we know that this is a function of both x and y, and what we're trying to figure out is if I could rewrite it this way as well. So we'll just do that. Everywhere where we see y, we replace it with ty. Everywhere with x, we'll replace it with tx. So this will be tx here times ty squared, all that raised to the 1/3. Of course, here this is t squared y squared over t squared xy in the first term. In this second term, looks like let me do everything on the inside first. So this will be t squared y squared here. So this will be tx plus t squared y squared, and all that raised to the 1/3. And just by kind of looking at this, I think this is going to be a little bit too messy for it to be homogeneous, but I'm going to go ahead and work it out anyway. And let's see, here we have t cubed times x plus y squared, all that 1/3. All right, and so then if we raise all these to the 1/3 power, we just end up getting t x raised to the 1/3, and then y raised to the 2/3. And so of course, we can see easily here that this is not going to be homogeneous because I'm only going to be able to factor out t out of the denominator out of both terms, but t squared the numerator, and that's not going to allow me to get back to where I originally was. So we know that this is not going to be equal to that. So it is not first order homogeneous. All right, so the next set of examples that I'm going to do are going to be examples where we know that they're homogeneous, so we're not going to go through this whole process here, but we will go through the process of actually solving the homogeneous equations for their solutions. All right, so this will be the first example where we will actually solve our homogeneous equations for solutions. we already know that all of these are homogeneous. So what we want to do is solve them for for all the solutions. And that means both constant and non-constant solutions. And we want to express our final answer explicitly as a function of x whenever we can do it. So since we already know that this particular first order ordinary differential equation is going to be homogeneous, that allows us to be able to make the substitution that u is equal to y divided by x, which in turn means that y is equal to ux. And I'm writing it both ways because depending upon what our differential equation looks like, it may be advantageous to use the u, maybe advantageous to use the y is equal to ux, or maybe both simultaneously. In this case, it looks like it would make sense for me to utilize the y is equal to ux here. Okay, so y here, ux minus x, y is ux plus x. And of course, once we have this, then it's just a matter of trying to rewrite everything in terms of u and x. So since I have y here, I also need to find out what dy over dx is in terms of u and x. So this would be dy over dx. And here, of course, since u is considered to be a function and x is considered to be a function, we will use the product rule here. So we'll say the derivative of the first with respect to x times the second plus first times derivative of the second with respect to x, and that's just 1. So we'll just leave that being u here. So what this means for us here is that the left-hand side of this equation, dy over dx, I could replace that with du over dx, x plus u. Okay, so I'm going to go ahead and do that now here. So here we have du over dx times x plus u. And so left side, right side, that's what that would look like. And so now all we need to do is just rearrange everything in terms so that we can get it into separable form. Okay. Now, of course, since we went ahead and did this substitution here, we know that we could factor out the x both out of the numerator and denominator. And of course, these x's will reduce to 1. So this tells us that our du over dx times x plus u on the left side is actually going to equal to u minus 1 over u plus 1 on the right hand side. And from here, we're just trying to get this into a form to where we can make it look like a separable equation. And then from that, solve it for u, substitute back in what u was, which is y divided by x. So let's go ahead and do it. So here I'm going to subtract u from both sides here. So I'll have du over dx times x equals u minus 1 over u plus 1 minus u. And here, since I'm going to need to subtract both of these, I'm going to have like denominators here. So what we can do is force that to happen by multiplying the numerator and denominator of this particular fraction here by u plus 1, because the u can be understood as u divided by 1. So doing that, this right-hand side here would just be u minus 1 minus u squared minus u, all that over u plus 1. Okay, and I'm just taking the minus u that's right here and distributing it to both terms. So here this would end up being, since I have a -1 minus u squared in the numerator, I'll factor out the negative, and we'll just say this is minus 1 plus u squared over u plus 1. And so from that, we see that du over dx times x is just minus 1 plus u squared over u plus 1. And so at this point, you should be able to see real clear that this is a separable ordinary differential equation of the first order. And so if we do some rearranging here, we'll see that we have u plus 1 minus, and then 1 over u squared du. And then on the right-hand side, we'll have dx over x once we do all of our algebraic manipulation there. And so at this point, we see that, yes, it is separable, and all I need to do is to integrate both sides. So in integrating both sides here, you can see here on the left-hand side that it's possible for us to use substitution rule to solve this. Of course, on the right-hand side, we see that that's just going to be natural log of absolute value of x, and then plus some constant here. So our main concentration here is that we want to work on this left-hand side, and to make life a little bit more simple for us, since we got to do more work on the left than on the right, I'm going to place this minus sign from being on the left side to the right side. Okay. So let's deal with this left-hand side first here. So therefore, integral of u plus 1 over 1 plus u squared du. We could separate that into two separate integrals here. Now, for the first integral, and I'm going to change colors here. So for this first integral, if we let w equal 1 plus u squared, then that means that dw is going to be equal to 2u du. And here we see that we need to replace u times du. And of course, we can easily get that by just dividing both sides by 2 here. Okay. So we see that all of this here is just going to be 1/2 of dw. And of course, all of this is just going to be w. For this particular integral, we know that the antiderivative of 1 divided by 1 plus u squared is just going to be tangent inverse of u, or arctan of u, if you want to name it that way. So we pretty much know what this is going to end up looking like now. So over here, we just have a 1/2 of dw over w, which is going to be, when we take the antiderivative of that, it's going to be 1/2 of natural log of absolute value of w. And then this will be plus tangent inverse of u. And of course, w here is just going to be 1 plus u squared. So we will substitute that back in as needed here. Let's clean that up because that's looking a little messy. So we have to refer back to this later. Well, I was trying to change the color, but that didn't work. Oh well. We'll move on. All right, so once we're here, then we have everything that we need here. Only other thing that I want to do is, since we have this 1/2 on the outside, I'm just going to go ahead and bring it here on the inside to make this w raised to the 1/2, which is the same as square root. So we'll do this. And then, of course, our w again is just 1 plus u squared. All right, so now that we have all that, then this means that integral of u plus 1 over 1 plus u squared du equals integral of minus dx over x. That implies that on the left-hand side, I'm going to have all this business here. Natural log of absolute value 1 plus square root of 1 plus u squared plus tangent inverse of u. And then on the right hand side, this will be a minus natural log of absolute value of x plus a constant. And so from there, to make simplification easy, we'll get everything with natural log on the same side. Use our logarithm properties to simplify as much as possible, and then figure out, and then we'll actually substitute in u to be y over x, and then figure out what y is. All right, so from this point, I'll have natural log of absolute value of 1 plus u squared plus natural log of absolute value of x, and this will be c minus tangent inverse of u on the other side of the equation. And here we can simplify this to just being natural log of absolute value of x times 1 plus u squared. And this will be c minus tangent inverse of u. And at this point, what we could do is we really want to get rid of all this, so we can do what we can here to try to separate this. But I think we probably want to go ahead and substitute in y over x for u, because that may help us to be able to simplify some more. Because right now it doesn't seem like we can do much with what we have. So we'll go ahead and try that out. So here we'll make note pen is acting up again. So we'll make note here that u is equal to y divided by x. This will imply that for here, have natural log of x times square root of 1 plus, and this will be y squared over x squared here. And this will be c minus tangent inverse of y divided by x. And here, what we'll see is that this 1 here could be rewritten as x squared over x squared. So because of that, that will make everything that's under the radical here, we'll be able to rewrite this as x squared plus y squared over x squared. And if you look here, if we take this square root here and just do it to each, the numerator and denominator separately for this, have square root like that, square root like that, and for this particular situation, we would have x divided by absolute value of x here. So this would simplify. So I think a better way to do it is just to rewrite this out like this again. So I'm going to say this is just natural log of absolute value of x plus, and then over here, this will be natural log of absolute value, all this business here, and we'll have minus, and then square root of x squared is itself absolute value of x. So we'll have that. And also notice here that since I have square root of something, it always has to be non-negative. So these absolute value signs that I have here, once I cancel these two terms here, I'm going to stop writing the absolute value because I'm not going to need it anymore. Okay, so now these two terms cancel to 0, and then I just have natural log of x squared plus y squared, and that's equal to c minus tangent inverse of y divided by x. And so in this case, I don't think there's going to be much left for us to do as far as, rewriting it in a way that would be, nice. I do need to put this square root here because I did forget that. So let's do that. So the only other thing I could possibly do here is realize that, of course, this square root here will give me a 1/2 on the outside. So let me see if I can erase that. Nope. Not going to allow me to do that real simple, so I'm not going to worry about it. So I'm going to come back here. All right, so here we're just going to have 1/2 x squared plus y squared, and I'm going to go ahead and add tangent inverse of y over x to both sides here. Let that equal to some constant. And last thing I could do here is just multiply both sides by 2. If I was to do that, then 2 times 1/2 would just be 1. So this would go away. Over here, instead of that being just tangent inverse, that would be plus 2 tangent inverse. And over here, this would be 2 times c. And I'm just going to say, let that be some other constant b. And so this would be our final result here. No need to try to solve this explicitly for y, because if we did, y is going to be defined in terms of x and y anyway. So it really doesn't help us to go ahead and rewrite it any other way. So we'll leave the answer as is here. So this will be our final answer for this particular example. And again, you can leave this as 2c, or you can rename it any other, constant that you want. All right, so what we have here, this final answer is going to be our non-constant solution, okay? So if we go back to the beginning of our problem here, please notice that we do not have any constant solutions. And the reason why that is because here, in order for us to have constant solutions, we have to have our derivative equal 0. The only way that dy over dx is going to equal to 0 is if y is equal to x. But x is not a constant. So because of that, this particular ODE, it's impossible for it to have constant value solutions. All right, so now let's move on to our next example. All right, so our next example, again, we're already given the fact that it's going to be a homogeneous first order ordinary differential equation. So we know that we can make the substitution of u is equal to y divided by x, or more conveniently, y is equal to u times x, where u is a function of x as well. And this implies that dy over dx is going to be equal to du over dx times x, if I take the derivative of the first times the second, plus derivative of the second, which is just 1 times the first. And so now, knowing this, what we need to do is rearrange this particular equation so that we have dy over dx equals, and then some function of both x and y. So if we do that here, we see that we're going to have x plus square root of xy dy is equal to y dx. And then from that, we'll have dy over dx. And here we'll have y over x plus square root of xy. And so this is the form that we need to have it in so that we can go ahead and make our substitutions. So our dy over dx is just du over dx times x plus u. And on our right side, everywhere where we see y, we can just replace it with ux. So I have ux here, x plus square root of x times ux. And this right side, keep working on it. It's just x plus square root of x squared u. All right, so now that we have that, this just means that our du over dx times x plus u is equal to, and here we'll have ux over x plus, and of course I can split this up, and square root of x squared. Here, normally I would say this is absolute value of x, and I'm going to write that. But we can simplify it to just x here because of something that we've actually seen in our original equation here, and I'll address that in just a second. Okay, so we have this situation here. Now, note in our problem that we had this term here, so square root of xy, which we could rewrite as square root of x times square root of y. And so what this implies is that both x and y have to be greater than or equal to 0 here. Okay, so in other words, x and y both have to be non-negative, and for that reason, that is why this absolute value of x here could just be rewritten as x. So we'll go ahead and put that in a different color here. Let's say that that is just equal to x, and this is the reason why. So now that we know that, we have du over dx times x. So let's rewrite that whole left-hand side here. And here, since we have x in both terms here, I should be able to go ahead and factor out an x out of numerator and denominator. And when I do that, I'm just going to have u up here, and I'm just going to have 1 plus square root of u down here. Because of course I got a common factor of x, both of these terms, x here. So if I factor the x's out, they'll reduce to 1. All right. So now from here, du over dx times x is equal to all this business here minus u. And then from here, kind of like how I've done before, I can force this to be a common fraction here by saying 1 plus u over here divided by 1 plus u. And this will end up being u minus u times square root of u. All that over 1 plus square root of u. Of course, these cancel. So from that, we end up having du over dx times x plus u. And all this business here, just on the right-hand side, just ends up equaling negative u square root of u over 1 plus square root of u. No, wrote something wrong here. This shouldn't be here. Yeah. All right. So yeah, that shouldn't be there. Yeah, because we already subtracted u from both sides. All right. So now that we have that, a little messier than some of the other examples, but you see that this is clearly a separable first order ODE. And so if we rearrange this to get all terms with u on one side, all terms with x on the other, then it's going to look like this. So we're going to have 1 plus square root of u over u times square root of u. On the right hand side, we'll leave the negative here, and this will be dx over x. Okay. And of course, here, what u times square root of u is actually u times u raised to the 1/2, which together this will be the same as u raised to the 3/2. Okay, so I'm going to rewrite that because it's going to help us be able to simplify here later. So this is u raised to the 3/2, and our square root of u here, this is going to be u raised to the 1/2. And of course, left-hand side now will just be u raised to the negative 3/2 plus u raised to the 1/2 minus 3/2, which is just u raised to the minus 1. Okay, and so it's a little messy, but this is not something that's too bad to deal with. And of course, I think I forgot my du here, so I need to go ahead and write that. So I knew something looked strange here. So you got your du here, equal sign. And you gotta have all that there. So it's du equal sign and then a minus. And so from this point, we should be able to just go ahead and integrate both sides with respect to their respective variables here. So just do that. And so now we'll go ahead and take it on home. So here on the left side, we'll end up getting u raised to the 3/2 plus 2/2 over same. u raised to the 1 is the same as 1 over u. So I'm going to go ahead and rewrite it that way. And of course, the antiderivative of 1 over u du is just natural log of absolute value of u. And of course, on the left-hand side, this will be negative natural log of absolute value of x plus some constant. And so from here, of course, what's on the bottom here is just going to be a negative 1/2. So the reciprocal of a negative 1/2 is going to be a negative 2. So this would be 2u raised to the negative 1/2 plus natural log of absolute value of u. And pen starting to mess up again. And I'm going to go ahead and add this natural log over here on this side and just have the constant there. So now at this point, what we want to do is go ahead and substitute in that u is equal to y divided by x. So here we want to go ahead and recall that u is equal to y divided by x. And that implies here that we have minus 2 y divided by x raised to the negative 1/2 plus natural log of absolute value of y divided by x plus natural log of absolute value of x equals this constant here. So if we simplify here, we see that we'll have negative 2 here, and y over x raised to the negative 1/2 is the same as x over y raised to the positive 1/2. We could rewrite natural log of absolute value of y over x as natural log of y minus natural log of x plus natural log of x equals c. And of course, those two terms will cancel to 0. Here we can further rewrite what we have here as a negative 2 square root of x over square root of y. And this will be plus natural log of absolute value of y equals some constant. All right, so now at this point, again, we want to try to solve for y as best or as explicitly as we can. One thing that I'm going to go ahead and do here is go ahead and multiply both sides by a negative 1, just to make what I want to do here later a little bit more clean. So we'll come here and multiply both sides here by a negative 1. And so in doing that, the left-hand side will end up being 2 times square root of x divided by square root of y. We'll have a minus absolute value, natural log of absolute value of y, and this will be a minus c. And if I go ahead and add natural log of absolute value of y to both sides, then I'll have this here. And this will be a minus c plus natural log of absolute value of y. All right, and so from here, at this point, what I could do is I could go ahead and just square both sides here. So if I do that, then I'm going to get 2x over y. and this will be equal to, I'm going to call this D plus natural log absolute value of y. And D is just going to be minus C here, okay? Also note that at this point, if I remember back at the beginning of this problem, one of the things that we said was that X and Y were both non-negative. So what this tells me here is that even though I'm writing absolute value of Y here, I can actually drop the absolute value signs, okay? So in my next step, I'm going to do exactly that. So here, I'm going to say that I have, let's see how I'm going to do this. If I multiply both sides by y, I'll have 2x here, and then I will have y times d plus natural log of y, like that. And yep, looks like I forgot to square this 2 here. Yep, I did. So this should be 4. And this should be a 4 here. All right, so yep, and so that could look like that. And this side here, yeah, this needs to be squared as well. I forgot to write that. So this needs to be squared here. Yep, so squaring both sides, 2 squared is 4. Square root of x squared is just x. Square root of y squared is y. And of course, all this side here is just all that squared. And we'll just say here where d is equal to minus c. And again, I just did that to make things look a little bit easier. You could very well have just said natural log of y minus c, and that would have been fine too. I could have left the answer that way. Just try to leave out negatives whenever I can. Okay, so that's the reason why I'm renaming them. All right, so this is probably the best that we're going to be able to do as far as a solution is concerned. Since y will be defined in terms of y anyway, doesn't really help us to try to manipulate this to write it any differently. So we know at this particular point that we have our non-constant solutions here. So let's go back and see, does it make any sense for us to have any constant solutions? Okay. So if we go back to our equation here, if we see this form, notice that we got y in the numerator here. Okay. So having y in the numerator there, if we let y equal 0, this lets us know that we actually have a constant solution. Okay. So here, by having this lets us know that y equals 0 is a constant solution. So what that tells us here is that this is not our only solution. So this is the non-constant solution. Now the actual constant solution is just going to also be y equals 0. So and y equals 0. And this will be the constant solution. And so both of those solutions will end up being what our solution to this particular differential equation is. All right, let's move on to the next example. All right, so our next example, we have here that we got x times dy over dx minus y is equal to square root of x squared plus y squared. And here we put the stipulation that x is going to be a negative number, okay? And so I did this just to make the problem a little bit easier to deal with. So first thing we want to do here, since we know that this is a homogeneous first order equation here, we want to get it into the form of dy over dx. And of course, you see with some algebraic manipulation, this is what that looks like here. Now, before we continue here, I know I've been looking at the constant solutions for these ODEs after we found the non-constant ones, but I'm going to go ahead and worry about that now. So if you look here, notice that there's not going to be a value of y on its own that we can plug in here to make dy over dx be 0. If it was possible, then that means that this expression here would have to be equal to a minus y. And unless y is negative, that's not going to be possible. Also, doesn't matter whether y is negative or not, we have to look at real number values of y that would just make everything go to 0 here on the right hand side. And we know that that's just not going to be possible because we have this particular expression here dependent upon x, okay? And if, of course, if we looked at it this way, y would have to be square root of x squared, minus square root of x squared plus y squared. And again, that's not a constant value because x could be anything that's a negative number. So we know for that reason we have no constant solutions here, okay? Now, of course, I'll go into a little bit more detail on this, basically writing out what I said as to the reason why we can't have any constant solutions here. But the main idea here is that we don't have any constant solutions. It's just not possible for this. So now we're going to look for non-constant solutions. And so since we know that our ODE is homogeneous of the first order, we let u equal to y divided by x, which means y is equal to u times x. And of course here, that means that our dy over dx is just going to be du over dx times x plus u, same as it's always been for the last few examples. And we're going to plug in our expression for dy over dx and y being u times x into our first order homogeneous differential equation. So if we take this expression here and we actually do that, this is what we end up having. And so now our goal from this point is to basically simplify and show that, yes, this equation here is actually a separable first order differential equation. Okay? So now we go ahead and start that process here. So first thing is, since we have x squared in both terms, I know that I could take the square root of x squared out, which is going to be absolute value of x. And so notice here that since x is assumed to be less than 0, that what absolute value of x is going to be is actually minus x, okay? Because if x is negative, then I have to have a negative multiplied by a negative to make this non-negative, okay? So have that in play. So the next thing, of course, is that these two x's here would reduce to 1, which you see that here. The left-hand side of the equation stays the same, so that stays the same. It's working more on the right-hand side, and this is what that would end up looking like. From here, we know that, notice that we have a plus u, so we're going to subtract u from both sides here, and that will cancel the u and a minus u. That would cancel. So I just have du over dx times x. Cancel, just end up with negative square root of 1 plus u squared. So once we're here, you definitely see that it is a separable equation at this point. So we rewrite everything to where we have everything in terms of u on one side, everything in terms of x on the other. And so here, when we try to integrate both sides here, my note here is just basically saying that we're going to have to use trigonometric substitution from a second year calculus course to be able to evaluate that particular interval. Okay. So I go through the whole process of actually doing that. So most of what I'm going to be writing here and talking about for the next few minutes is just me trying to evaluate what this particular interval is. So here we note to try to figure out what type of trigonometric substitution I need. We're thinking about, all right, well, what plus some trig function squared gives me another trig function squared. Okay, and here we can see that tangent squared plus 1 gives me secant squared. Okay, so that means that 1 plus tangent squared is going to give me secant squared. So our substitution here is going to be a tangent of theta in this case. So we're going to use the fact that 1 plus u squared equals to 1 plus tangent squared if u is equal to tangent theta. So that's the trigonometric substitution that we're going to do. And our goal here is to use that trigonometric substitution to get everything rewritten so that we can actually do the integration. And then after we're done, we're going to take the algebraic representation of our trig functions and substitute that back in so that we can get an algebraic answer instead of a trigonometric answer. So once we do that here, if we let u equal to tangent theta, then of course the derivative of u with respect to theta is going to be secant squared theta. And then of course rearranging this, du is just secant squared theta d theta. We also know here that if I go ahead and make that substitution, then 1 plus tangent squared theta is going to be secant squared theta. And if I take the square root of all that, what I end up with is the absolute value of secant theta here. You can't see the absolute value sign, but it's there. And so now we go ahead and substitute everything here. So this du that you see here is just secant squared d theta. So that's what goes on top. The square root of 1 plus u squared is just absolute value of secant. And so if I substitute everything in, then of course secant squared, I could rewrite this as secant squared theta times secant squared theta and make that absolute value. This is an equivalent statement here. So with this, I know that these absolute values of secant thetas would reduce to 1. And I just have one absolute value of secant theta left. And so the absolute value part is important because, again, we're only considering the values of theta in this case, where secant is going to be non-negative. Now, of course, a lot of this makes sense here because, remember, we're trying to take secant theta and translate it into something that's algebraic. And remember that secant is the reciprocal of cosine, okay? And what cosine is, we really think about what cosine is, cosine theta, it is going to be the adjacent side of some right triangle divided by the hypotenuse. So it's a ratio of sides of a right triangle. And right triangles, the lengths are always positive. So in this sense, even though I have this absolute value of secant squared here, and technically speaking, I can drop it because of the fact that I know that what it is that I'm actually talking about is something that's algebraic, and both numerator and denominator here would have to be something that is non-negative. Okay, so as I go through all that, I eventually get to that point here. But of course, we know that we said that u was equal to tangent theta. Okay, so once we're here, we already know that the antiderivative of secant theta, since we know that absolute value of secant theta is going to be the same thing as secant theta, is just going to be this. So we already know that part. Okay. All right. So here I'm doing this more so to be able to do the algebraic translation later. So we know that tangent theta is equal to u over 1, which is the same as opposite over adjacent. So opposite over adjacent to the angle theta. And of course, if we use what's better known as the Pythagorean theorem, we get this square root of 1 plus u squared here. And of course, u1 square root of 1 plus u squared and u plus 1 are all greater than 0, okay, because we're talking about sides of a right triangle. Therefore, your secant theta, that's just going to be the reciprocal of cosine. Cosine is adjacent, which is 1 over square root of 1 plus u squared. So reciprocal of that is just the opposite, which is just going to be square root of 1 over u squared. Okay. So we say all that. And even though I really didn't do it here, actually I did. So I did it here. So I went ahead and dropped this. But whenever we do the antiderivative of secant theta, we do have these absolute value signs here that we got to put back on. Okay. So technically, again, we could, take them off, because since secant theta is always going to be non-negative, tangent theta is always going to be non-negative in this sense, then of course the sum of those two will also be non-negative. But we just keep on going here. So once we have this, then let's go back here. Yeah. So once we find out what the left-hand side of this particular equation is going to be, we have what our answer is in terms of trigonometric terms. But now what we need to do is figure out what this is going to be in terms of algebraic terms. Okay. So what is it in terms of x? So again, we made these translations here. And right now, according to our right triangle, we need to rewrite everything in terms of u. And then after we get everything in terms of u, then we can rewrite everything in terms of y or x. So that's what this step right here is basically trying to communicate. So we're trying to remember what secant theta is, what tangent theta is, all in terms of u. So we go and we replace secant theta and tangent theta in terms of u. And so now we are finally back to basically trying to get to a solution to this separable equation that we started off with about 5 minutes ago. And we know that the left-hand side is equal to all of this. Right-hand side is just equal to this. And so now from here, we'll go ahead and substitute that u is equal to y divided by x, and that y is equal to u times x. And we go ahead and substitute in. And so from this point, it's just a matter of us trying to do what we can to simplify this as much as possible. We take this 1 here and rewrite it as x squared over x squared, so that we have this expression here. And then, of course, from our logarithm properties, we have log of something plus log of something else. We can multiply that together here. And if we do that, then of course, x gets multiplied to both of these terms here. And you see that. So from here, this square root of x squared, this is going to be absolute value of x, which since x is negative, that would be a minus x here. And that's how whenever we have the x and the x here reduced to 1, that's how we end up having the minus being left here, okay, in that term. Of course, for the second term, y over x times x is just y. And then here, what I did is just switch these two terms inside the absolute value signs around, and then turn this equation into an exponential one. And then from there, we're pretty much on easy street from that point. So here, e raised to the natural log of absolute value of whatever this is just absolute value of whatever that is, equals e raised to the c. And then, of course, from here, from our absolute value properties, if we make this go away, then this has to be plus or minus. And of course, here that would just say that y minus square root of x squared plus y squared is equal to a, where a is equal to plus or minus e raised to the c. And then, of course, final answer here, y is equal to a times square root of x squared plus y squared. If you want to make this equal to a constant, then we can do that, or you could leave it this way. Okay. Either way ends up being the final general solution for this particular homogeneous ODE. All right, so for our final example here, we have another homogeneous equation. Again, our goal is to get this thing into dy divided by dx equals something form. So we'll go ahead and take care of that now. And I'll go ahead and do this first. We also know that u is going to be equal to y divided by x, which means that y is equal to u times x. So we have that. If I go ahead and rearrange this, then this would be x times dy, and that would equal to minus x plus y dx. And from here, this would be dy over dx. And this would be a minus xy over x, which would actually be a minus 1 plus y over x, like that. All right, so now that we have all that business here, we know what this particular equation is going to look like. We know that y divided by x is u. We're going to need dy over dx in terms of u, so we need to go ahead and find that. And that's going to be du over dx times x plus u. So therefore, our dy over dx equals to negative 1 plus y over x is essentially going to be du over dx times x plus u. And this is going to be minus 1 plus u. And then from here, if we subtract u from both sides here, then we're going to have du over dx times x equals to minus 1 minus 2u. And then again, here you can see that this is clearly a separable first order ordinary differential equation. And we'll write everything in terms of u on one side, write everything in terms of x on the other. And to make life a little bit more simple, again, I'm going to take the negative off of here and apply it to here. So that's going to make this plus, and I'm going to make that go away. So I'll just rewrite it. All right, so now that we have that, then we know that all we need to do now is just integrate both sides. And here, to integrate both sides with this situation going on here, we will need to use substitution rules. So I'll go ahead and write that in now. So let w equal 1 plus 2u. So that means that dw is going to be 2 times du, which means that dw divided by 2 is just du. All right, so now that we have that established here, then of course du is just going to be 1/2 dw over w. And on the other side here, minus dx over x. And this is just 1/2 natural log of absolute value of w equal minus natural log of absolute value of x. And then this will be plus some constant here. From this point, here we know that the 1/2 natural log of absolute value of w, that's the same as natural log of absolute value of square root of w. I want to go ahead and add the natural log of absolute value of x to both sides here. And that will just equal to constant. So here, because of our logarithm rules, I could rewrite this as just natural log of x times square root of w equals c. And then turn this into an exponential equation by letting the base be e. Therefore, we have absolute value of x times square root of w is equal to a. And this means that x times square root of w will be equal to plus or minus a. Oh, sorry. Nah, I meant to write that as e raised to the c. Yeah. So this is e raised to the c. And this is e raised to the c. And that is equal to a. All right, and so now from all of that, what we essentially have here is that x times square root of w is equal to a. And recall here that w is 1 plus 2u. So this is x times 1 plus 2u equals to a. And recall here that our u, if you remember, is just y divided by x. And of course, from here, we have that, let's see, how can we do this? I could make this 1 here, x divided by x, but then that would actually make things a little bit more messy, so don't want to do that. So what we'll do here instead is I'll just go ahead and divide both sides here by x. So this will be 1 plus 2y divided by x, which is equal to a over x. And then we'll square both sides here. And this will end up being 1 plus 2y over x, which is equal to a squared over x squared. And then from there, we will just solve for y. And we'll start off by subtracting 1 from both sides. So, yep, this will be a squared divided by x squared minus 1. And then from there, we'll just multiply both sides by x divided by 2. Yeah. So I'll just go ahead and rewrite that and finish that up. My pen, please work for me. All right, so a squared divided by x squared minus 1. And here we're going to multiply by x divided by 2. X divided by 2. And that will give us y on the left side. And if I go ahead and distribute through, I'll have a squared times x over x squared over 1/2 x. And here I could simplify this by making a squared equal to some constant k, and 1 divided by x squared will just, x divided by x squared would just be 1 divided by x. So we'll have the situation here. So finally, our final answer here would be k divided by x minus 1/2 x, where k is equal to a squared, which that is equal to plus or minus e raised to the c squared, just to make sure we're tracking everything. And of course, c is going to be just some real number. So this would be our final answer here. And we've talked about the non-constant solutions here. So again, for the constant solution, again, we have a situation here where the only way that dy over dx is going to be 0 is if y is something that is not a constant, negative x to be exact. So because of that, we know we have no constant solutions. And we know that this is the only answer. All right, and so this concludes the second video on homogeneous first order equations. Hope to see you around for part 3, which will be covering Bernoulli equations.